this is LabRat's Engineering YouTube channel. Tech Talks Lecture 120, Designing with a Zener Diode. A Zener diode's purpose is to maintain a stable, constant voltage across itself when operating in reverse bias breakdown, making it ideal for voltage regulation, voltage referencing, and overvoltage protection in electronic circuits. It achieves this by allowing current to flow in the reverse direction at a precisely controlled threshold voltage, known as the Zener voltage, without being damaged. The current diagram shows the schematic symbols for the Institute of Electrical and Electronic Engineering, IEEE, as well as the International Electrotechnical Commission, IEC. The IEEE is an American 501 charitable professional organization for electrical engineering, electronics engineering, and other related disciplines. The IEC is a global organization that publishes international standards for all electrical, electronic, and related technologies. The diagram you're looking at now shows the IEEE schematic symbol for the Zener diode and the IEC schematic symbol for the Zener diode. As you can see, these are forward bias. So you have a positive voltage on the anode, a negative voltage on the cathode, and yes, it will conduct just like a regular silicon rectifying diode. The symbol's a little bit different for the IEEE symbol. It looks like an S, symbol like an S, and then the IEC is like a backward L. You can see a rendering of a manufactured Zener diode, and the line is on the cathode side. And then to the diode to the far right is a diode, Zener diode, and reversed biasing. And do this, reach the breakdown Zener voltage, and it will conduct, and it will be a good reference, voltage reference. The diagram now that you're looking at, it shows you the schematic layout that we're going to be using for the design of this Zener diode. The resistor is limiting the current going to the Zener diode, and then we have the voltage supplying the energy for the Zener diode, and our output will be across the Zener diode. The diode is a 1N4733A Zener diode, which puts out a 5.1 volt reference, plus or minus 5%. The key applications for the Zener diode are voltage regulation. By connecting a Zener diode in parallel with a varying input voltage and in series with a resistor, it provides a stable, constant output voltage equal to its Zener voltage. It is also used as a voltage reference. Zener diodes are used to provide stable reference voltages for more complex circuits such as a power supply and ICs by generating a stable voltage point. It's also good for over voltage protection clipping. When a Zener diode is used in parallel with a sensitive component, it clips or diverts any voltage spikes that exceed its Zener voltage, preventing damage from the event like electrostatic discharge, ESD. Surge suppression. Similar to over voltage protection, they can be used to absorb transient voltage spurs, protecting the circuit from damage, and also can be used for switching applications. Under specific conditions, Zener diodes can act as a voltage triggered switch, activating at their specific breakdown voltage. How it works. First, we go over the forward bias. Like a standard diode, it allows current to flow freely when the voltage is applied in the forward direction. As you can see in the Cartesian plot, once the VF forward voltage reaches that of 0.3 for germanium or 0.7 for silicon, we have a forward bias conduction, which we'll see in the lab as we see the needle deflect as we forward bias the Zener diode. Reverse bias In the reverse bias, it blocks current until the applied voltage reaches the Zener voltage. We have a 1N4733A, which has a Zener voltage of 5.1 volts. Once the Zener voltage is reached, the diode enters a reverse breakdown state where current begins to flow in the reverse direction. This critical feature is that this reverse current flow is accompanied by only a very small and stable voltage drop, which remains almost constant even if the current or the input voltage changes significantly. We're currently looking at the electrical characteristics of the 1N47XXA family of Zener diodes. We are interested in the 1N4733A, which has a typical Zener voltage of 5.1 volts plus or minus 5%. That gives you the minimum of 4.8 and to a maximum of 5.355. The test current that they used was 49 milliamps. We will also use that. And then you have the rest of the diode, the information, the Zener, max Zener impedance of 7 ohms, the current, Zener current of 1 amp, 1 milliamp, the reverse current of 10 microamps. And so we'll design to these specs using circuit and figure 2. Observing the design specifications of the diode we just looked at, we can see that 49 milliamps is used, so we will also select a resistor that will limit the current to 49 milliamps and handle the power resulting from this action. We will follow the circuit in figure 2, and the voltage input to the circuit will be 10 volts DC. So now we'll open up our PTC Math CAD and do our calculations. Okay, we already opened up the PTC Math CAD, so we're going to kind of give this a title. We'll call it a text block. Let's see, designing a Zener diode. Oops. We need to declare our voltage in, which we'll call VDC in, shift colon, 10 volts. We need our units. Come over here, double click the V. Our current's going to be 49 milliamps. We'll call it I diode for current. Shift colon, 49 milliamps, excuse me. Come down in here, go to current, milliamps. We'll say R1, or we'll create R1, shift colon equals VDC N divided by IVIODE, current divided by the voltage. Then we'll say R1 equal sign. There's our resistance we need to get the circuit to maintain a 49 milliamp current. We need to know our power. So we take, say, P for power, shift colon equals current times voltage. So IDIODE has to be exactly the same, so it needs to be a capital M times VDCN then we say P equal sign equals 0.49 watts. So we need a half a watt resistor. All right. And that's it. That's our circuit. We'll get a 2.04 or 2.041. There's just a 204 ohm resistor. have a half watt value and put that in, and we'll build our circuit in the lab. That's it for the PTC. Let's do the QUCS simulation now. Thank you. Now for the QUCS, open up your QUCS by clicking on the batch file. I've already created this experiment or simulation, so we click on that. I'll show you where to get everything. So we started with the voltage. We go over to the libraries, or the components, go into the sources, DC voltage, I drag that over like that. I edited the properties, made it 10 volts, said apply. Then I went to the lump components, got us a US resistor, brought that over. I right clicked on it, edit the properties, made it a 204 ohm, 0.082. You don't have to do that, just make it 204 ohms. Then the Zener diode is a little bit different. So on the Zener diode, you have to go to the libraries, go to Z diodes. We know we have a 1N4733A. Clicked on that, brought it over, dropped it in, and then right clicked on it just to make sure it was a 1N4733A. This is using a special netlist file that's in the library of SPICE data. I wired it all together. I need a probe, so I go to the components. A probe, I got the voltage probe, brought that over, hooked up the positive to the cathode of the Zener diode. I get a DC simulation from the simulator, DC simulation, bring that over, drop it in. Then I need a table. Well, right after I did that, when I dropped that in, before I add the table, I came up here and hit the gear, made it do a simulation to make sure everything was connected correctly and it's going to work. Then I dropped in a chart tabular table, drop that in, and these will show up because I've already hit the simulator. If I would have dropped this in before I did the simulation, these would not be here. This would be blank. But once I hit the simulation and it calculates the nodes, then these get populated. And then I can select which ones I want to see, and they are brought over to here. I say apply, say okay. Now I don't want that because I already got it. Hit escape to get rid of that. All right, come up here and hit this. And I ran it again, and when I run it the second time, this gets populated, and we can see that the Zener diode in the simulation put out 5.05 volts. And so it's working, and that's within the 5%. Okay, that completes this lecture, and now let's go into the lab and actually build the circuit. Thank you. Okay, now we're in the lab, and we calculated that we needed a 204 ohm resistor with a 10 volt power supply to limit the current to 49 milliamps. So I'll show you that right now. We'll bypass the Zener diode, turn on our meters. This is on milliamps. This is voltage. We don't really need that, but we will use it to measure our input voltage. We'll turn on our power supply. We got 10 volts coming in. I'm going to put this here. And we get nothing. Oh. That is because the meter's not hooked in. Okay. There you go. We have, can't see it because of the glare. So we have 50 millivolts. we have measure the input. Got 9.93 volts in. And so that's our circuit. So our series resistance is correct to limit the current. This will be the maximum current you can get to the circuit. Now when we hook our Zener diode into this circuit, a funny thing happens. So let's hook the Zener diode into the circuit. We'll measure the output of the Zener. Make all our grounds correct. This will be directly off the output. So the circuit is coming into here. It's going into the current shunt meter, coming back out, going into the Zener. That's our power. We have, let's see. Here we go. So now it's been reduced to 20 milliamps because of the Zener diode's impedance. We got 5 volts, 4.92 plus or minus 5%, and which is having troubles auto ranging. But why is that? Well, that's because the Zener diode's depletion region is decreasing as the current goes up, which helps keep the voltage constant. So we have to calculate what the impedance is as it changes. So of course we would use the 5 volts and 20 milliamps. We would divide the 20 milliamps into the 5 volts up across the Zener, and that would give us our impedance. Then we add we calculate our impedance to be 242.4 ohms, and we add that 204 to the 242 and divide it into 10 volts, because that's the current into the entire circuit, and we get 22.4 milliamps out. Our meter's reading 20. The calculator is theoretical, so and that's not actually a 204 ohm. I have 4, 8, 100 ohm resistors. I remember I had to have a half watt power, so I paralleled the 200 ohms and put 4 of them, 4 pairs in series, making 200 ohms. So the resistance is not as high. So there it is. That shows you the Zener diode working, the current working, and how to calculate the impedance of that Zener diode over a range of current. We can change the range of current, and you can see how the current will change, but the Zener will stay the same. So now we went up to 25 milliamps. You can see that the Zener is still at 4.95, which is, that's within specs. Let me change it one more time. I'll really increase the voltage, the current I mean. There we go, 32.9. Now we're at 5 volts, 32 milliamps. Put that back there, that gets hot after a while. But there you go. That completes this lab. We have some more terms that we have figured out, and I will give that to you in the next slide. Thank you. There's a couple things I want to go over that we didn't cover, and that is from the spec sheet, the electrical characterization sheet. One of them would be the Zener voltage at the test current, IZ, also known as IZT. It is IZ here. In my college reference, it's called IZT. Here is your test voltage at IZ, which is VZ, or also known as VZT, which would be 5.1 volts. And that is, you can see that right here. The test current ensures a reverse breakdown and a steady state Zener voltage. So that's important. So as you'll see here, let me open this file up to show you where this takes place on your voltage, your Zener voltage graph to critical zone, which is right here. Now, your IZ minimum is going to be right here, IZ minimum. That is the 1 millivolt or whatever it takes to sustain the diode to be in Zener condition. Then IZ max is the maximum voltage that this can do in reverse current. This is your Zener breakdown region. This is your operating zone. IZT will be right here in the middle. Okay? So we have the impedance just below VC, which according to that graph, which I'll open again, that is right here. So VZ, the impedance just below VZ, ZZ is right here, as you can see. Now ZK, the impedance at the test current, which is the test current's going to be halfway through the Zener breakdown. That'll be right here. And that's the impedance that we calculated at the end of the lab there. And it explained why we went from, that was designed to be a 49 milliamp current, and it went down to 22 milliamps. That's because they had an internal impedance, which I think was 242 ohms. IZK is the minimum. We just talked about that will operate in reverse Zener. And IZM is the maximum current to ensure. IZM is right here. IZK is right here, as you can see. And then ZK at IZK is right here. IR and VR are leakage currents resulting from the reverse voltage below VZ. VZ, from here, this is VZ, that's your knee voltage right there. And then that current is whatever occurs back here. That's your reverse current right in here. Okay, that finishes this lab. I hope you enjoyed it. And we will continue to the next lab, be lecture 121. Thank you. Please select like and subscribe.